All right, we're going to take a look at some basic differentiation properties. We're going to learn a whole bunch of properties along the way, but for now, we're just getting into the early basics. So it's going to allow us to take the derivative of a whole lot more functions than we could before, and it's going to allow us to do them in an easier way than going through that definition of the derivative every single time we want to calculate a derivative, because the algebra can get really messy with those, and so it'd be nice to have a much easier way to do that. So for the next couple weeks, we're going to be developing tools that allow us to find derivatives easier than going through that definition of the derivative. We'll be able to find them much quicker and much easier. So here's the first of the rules that we want to look at. If you have a constant function, your derivative is equal to 0. And this makes sense if you think about it in terms of tangent lines. So if you have a horizontal line, right, that's what a constant function is. You've got your horizontal line there, right, just a sort of level line. What are the tangent lines? Well, they're all going to be horizontal lines, which are going to have a slope of 0. So when you calculate the slope, you'd expect to get 0. Turns out the entire function is 0. So it totally makes sense. Think about it in terms of a rate of change. What is the rate of change of a constant function? There is no change. So your rate of change would be 0. So both from a graphical perspective, a conceptual understanding, all of it, it really makes sense that the derivative of a constant is 0. Okay, so anytime you have a function just set to a specific number, right, a constant function, that derivative is going to be equal to 0. So if you run across something like, if your function is f of x equals 3, the derivative is equal to 0. If the function is f of x equals 5, the derivative is 0. If the function is f of x equals 0, the derivative's 0. So really easy to calculate. You'll get to the point where this is automatic. You don't even think about it. You just see a number. You're taking the derivative of a number. Boom, it's gone. It's 0. Okay, so that one's not too bad. Next one we're going to use pretty frequently is called a power rule. And so if we look at that, let's make sure we understand this, because we want to make sure we're... So here's a nice shortcut that we use when taking the power of a variable. So here's where you got to start being careful. The difference between your polynomials and your exponentials, the difference between 2 to the x and x to the 2. You want to be able to tell the difference between those, because this rule only applies to one of them. So this says that if your function is x to the n, we sometimes call those power functions, then your derivative is going to be where you bring the exponent down in front and you decrease the exponent by 1. Okay, so bring the exponent down in front, decrease the exponent by 1. And remember, this is applying to things like polynomial terms, right? That's what you have in a polynomial, x to some power. It's not like an exponential where you have 2 to the x. You can't use it in that case. So this is another one that's going to become kind of automatic for you. You're just going to automatically do it. And as you'll see, by the time we're done here, taking the derivatives of polynomials is really, really easy. So let's say we have this function like f of x equals x to the 7th. Well, then our rule says you bring that exponent down in front. So you can see the 7 is now down in front. And we've decreased our exponent by 1. So the derivative of x to the 7th is 7x to the 6th. Okay. All right, so what if you're taking the derivative of something that already has a value in front of it? What happens when we bring that value down? Well, if we have 3x to the 5th, well, our rule tells us that we should bring the 5 down in front, and it multiplies the 3. So that's where this 15 is coming from. It's the 3 that was already there times the 5 that you're multiplying of the exponent. So it becomes 15. We decrease that exponent by 1, giving us a 4. So 15x to the 4th. And it's nice, it works the exact same if you have fractions. So x to the 7/3, what do? You bring that fraction down in front, so 7/3, and then you subtract 1 from that fraction. So 7/3 minus 1 would be 7/3 minus 3/3, right? If you write 1 as a denominator with a 3, 1 becomes 3/3. So 7/3 minus 3/3 is 4/3. So 7/3 minus 1. So we end up with 7/3 x to the 4/3. Okay, so that's pretty straightforward. All right, so how do we start putting these together to take the derivative of something like a polynomial? And I've been telling you you'll like when we take derivatives of polynomials, and here's why. So a few more, I'm not going to write them out, but they're in the book in the blue boxes. if you look in there, we get a few more properties. One says that if we want to take the derivative of a function, we can break it up into the different terms. So the pieces that are separated by a plus or minus. Can't do that. When we were finding the definition of the derivative, this would be brutal to try to go through and do the algebra for finding the derivative for this function using that definition of the derivative. It would be rough. But you'll see when we're about to go through and apply the rules that we've just learned, it's super easy to take derivatives of polynomials. You're going to like when you have to take the derivative of a polynomial. So what that means is we don't have to plug all this into the definition of the derivative. We can take them one term at a time. Worry about the derivative of this first piece. Then worry about the derivative of the second piece, then the third piece, then the fourth piece, and the fifth piece. So there we're breaking it down into smaller individual problems that we can go through and calculate rather than trying to do the whole polynomial at once, which is convenient. So then we'll just go through and we'll apply that rule to each of the individual pieces. If we want to take the derivative of just this first piece, the derivative of 3x to the fourth is 12x cubed, right? You bring the 4 down, multiply by 3 to get 12, decrease the exponent by 1, you get 12x cubed. Now here, 5x cubed. So we bring the exponent down in front. 5 times 3 is 15. 3 minus 1 is 2. 2x squared. Bring the 2 down in front, giving us our 4. Now we get x to the 1, but we don't usually write x to the 1. We just write that as x, right? Same thing over here. We've got minus x to the 1, right? Remember, there's a little 1 here. We just don't write it. Well, if we bring that 1 down in front, we're multiplying by 1, so it doesn't really change anything. Decrease the exponent by 1. That gives us x to the 0. And remember, anything to the 0 is 1. Right? So the negative x just becomes negative 1. And of course, the constant function, when we take the derivative, becomes 0. Right? So that you actually lose that last term because we're not going to write a plus 0 on the end of this polynomial. That would be kind of silly. But here, we've just easily taken the derivative using our new properties, which make it much easier. Now, sometimes you have to find a derivative by taking the definition, right? The reason it's important is sometimes you don't have a nice clean shortcut for the particular problem that you're working on, and then you have to do it the long way. But for most of the problems that we're going to work on, we are going to have some type of property that makes it a little bit easier than to go through the entire definition of the derivative. That is the limit of the difference quotient. Remember those problems, and they're a total pain. We don't have to do that in this case.